Hello. Karen, start. A very good afternoon to all. Now we have amongst us our expert, Dr. Anil Kumar. I welcome you, sir, in this session. Dr. Anil Kumar received his PhD degree in Electronics and Communication Engineering from NIT Jalandhar, Punjab. He did his BTech degree from MD University Rohtak, Haryana, with specialization in Electronics and Communication Engineering, and degree of ME from CR State College of Engineering. Now it is called as DCR University of Science and Technology, Murthal Sonipat, with distinction in EI and C. His fields of special interest include soft computing and wireless sensor networks. He has published 16 research papers in journals such as Applied Soft Computing Elsewhere, AIS Journal of Springer, IJEE, and Proceeding of National and International Conferences. He has been a referee for IEEE Transaction of Computer Networks, IEEE Sensor Journal, and Soft Computing Computer Network by Elsewhere, and in national and international conferences. His professional experience includes teaching as associate professor in the Department of Electronics and Communication Engineering at Chandigarh College of Engineering and Technology, that is CCET, Chandigarh. He is a member of IEEE and also life member of Indian Society of Technical Education. So with these words, I would like to invite Dr. Anil and request him to kindly enrich our participants with his knowledge.
यहाँ पे बेस्ट रहेगा, कंफर्ट रहूँगा मैं यहाँ पे. थैंक यू. नहीं ऐसे कोई जरूरत नहीं पड़ेगी. Start. So very good afternoon, one and all. My name is Dr. Anil, and I am from Chandigarh College of Engineering and Technology in the Department of Electronics and Communication. Today, we will discuss in next 1.5 hours about the various issues which are facing in the embedded world. One of the main issue is how parallelly we can compute the data with minimum computational complexity and also with the maximum utility of the hardware efficient to make the hardware more efficient with the limited resources. Then we will further focus on some multimedia processor also, that how the GPU processors are there and making the complexity in the computation is very low. So today discussion will start with why the parallel processing we require. Then we will discuss some parallel hardwares, the parallel operating systems available and how we can work on the operating systems. Then we will discuss the programming paradigms, and then finally we will conclude with the challenges which we are facing in the parallel processing of the data in embedded world. Basically, what happened? A figure is in front of you, and you will find the basic computing element. We have some processor, and while processing the data, we require the number of processor, and then by requiring the number of processor, hardware is becoming very bulky, and the cost, not in the form of money but in the form of energy, the infrastructure wise, is increasing to handle the data, and the clock cycles we require to handle this huge data may be high. In the similar manner, to minimize the requirement, we go for the parallel processing. Somehow at the microkernel level, operating systems are available. Then we interface with the applications to to run the applications by using this parallel computing processor through the programming paradigms. So these are some basic computing elements which we take in the parallel processing. There are two era of the computing. One is a sequential era and another is a parallel era. If we consider the sequential era, then if we take an example of your simple microprocessor or in a microcontroller, where we just simply compute the data, and the basic architect of the simple you can see there the clock cycles we have at a single time, we can run only a single data, and the consumption of clock cycle is the same. But if we incorporate some parallel processing with an existing infrastructure, and suppose if we take an example that how the instructions are being fetched, or if we take an example of machine cycle, it is a combination of fetch cycle and the execution cycle. So while fetching the data and executing the data, the clock cycles are being consumed. If it is 1 byte instructions, then minimum 4 clock cycles are required. So if we take an example of in 8051, the pipelining is there, or in 8086. So in pipelining, what we do while data fetching, after fetching we go for the executing. So while decoding the previous instructions, the next instruction is fetched. So in pipelining is a parallel processing is going on, but it is not up to an extent so we can execute the complete data parallelly. So we can say here a new era arrived, some emerging area has been started, some new applications were involved, and we come forward with the parallel era. So earlier in the sequential era, we have some sequential architectures, some computers are being used, and we use the applications. But in parallel eras, we have system softwares, we don't depend upon the compilers, and we run our applications simultaneously. So let's start with the history of parallel processing. Parallel processing can be traced to a tablet dated around 100 BC. So very too long back we are using, since we are using this parallel processing very too long. So tablet has 3 calculating positions that infer that multiple positions, and the reliability of the speed is increased. We can be increased with this. So how we get the motivation to use the parallel processing with our data? Because it is required. Whenever we incorporate some new technology, it is the requirement that on the basis of requirement we incorporate or we enhance the existing infrastructures. So motivating factor for the parallel programming is that simple example I have just mentioned here, that just as we learn to fly, not by constructing a machine that flaps, it wings like birds, but applying the principle of aerodynamic. But the objective of applying this principle of aerodynamic depends upon the demonstrated by the nature. And we model the parallel programming after those of the biological species. Maximum technologies are being inspired by the nature, and a lot of applications are available which are being nature inspired applications. Then if we aggregated the speed with which the complex calculations carried out by our neurons, individual response is slow, but if we combine the complete response of our neural system, the speed is very high. And it is the best example that in our neural network or the neuron systems, we do a lot of parallel computing. So by motivating or by we get a motivation. We get a motivation from our neural brain system that how when we people are parallelly processing the thoughts in our brains, why don't we apply the same phenomena in our computer system? So there are a lot of feasibility, lot of possibilities are there that we can also do the parallel programming with the existing machine systems, and we people are using this. Why parallel processing is required? First, as I told you in the beginning, that we have to make a system which must have low computational complexity, because if the computational complexity is high, then the system will be overloaded, and we can say that the consumption of energy will be more, the accuracy may be affect the, so the overloading may affect the accuracy of the system. So we could say that the computation requirements are ever increasing day by day. Visualization, distributed database, then simulations, scientific predictions, and everywhere, because we people are playing with the data. If we take our simple example of a mobile, then we want to run this number of applications simultaneously, and we want to make it in a very handy. So while our processor, how the processor is being handled, and we are using the octa processor, we are dividing the dual processor. So octa processor means the processor is divided into this, we could say the different categories, and there we are running the application simultaneously. So we require to make to run the number of applications again and again or simultaneously. So to extract the simultaneous output, we need the parallel programming. If we consider the sequential are architectures reaching physical limitations. Just if we take an example of your wireless sensor network, and we are dealing with the sequentially, so speed of light is there, which affect, because we could say that the line of sight problem is arising with there. So then the thermodynamics effects, temperature are affecting. So a lot of issues are there which needs to enhance the processing, that the parallel processing is required to handle the bulk size of the data, even though we are doing the clustering even with our instruments, machines, so that data can be handled parallelly, efficiently, and speedily. So whenever we design any system, it is required that system must be provide accurate output. Along with the accuracy, system must be efficient with the advancement with the emerging technology. Then the system must be scalable. Scalability defines in terms of that the data may be small or huge or a very bulky data, but that system must perform accordingly and efficiently. Again, the how we are growing how the growth system of an human is being, we consider that here you will find here that we are increasing our height vertically till the age of 18 to 17 year, but once we cross the age of 70 or 18, you will find that we are, instead of vertical, we are increasing horizontally. So here you can see that how the vertical growth we had achieved and up to an extent, but as we are increasing horizontally, that you can say that how that these things are to be handled, how the now data is increasing vertically, horizontally, then along with this it is also increasing vertically also. So this is an example that how the people are how to handle that particular growth, either vertically or the horizontally is required. So here we have the computational power improvement example is there. If we take an example of two processor here, the processor 1 is there and the processor 2 is there. Processor 1 may have the low frequency, whereas processor 2 has high frequency. Then and then we compute. But the thing is that the computational complexity is not being handled, though it is increasing. If we make a cluster of these, even though we required high clock cycles, the frequency, more frequency is required, power consumption. But if we kernel all these processor in a single hardware, and if we do the segmentation of our existing structure, and that segmentation is assigned to the different frequency, or the same frequency can be assigned to each segment, and the segment may be asked that you can perform this task, this, and the memory segmentation we can also be used. So by using the segmentation of the processor, and we can define this multiprocessor, we can enhance the speed, we can minimize the computational complexity, and we can handle the data parallelly. And so if we are handling the data parallelly, we can have a number of applications at a time. So again, why we need the parallel processing, the technology of parallel processing is mature and can be exploited commercially, and we are doing right nowadays. Significant, lot of research and development work is being required, lot of tools are available, and environments we are creating. So significant development in networking is also required, because nowadays we people are the part of a huge network, where we are just not in a homogeneous network, but we have a lot of heterogeneous network, that a data of a highly bulky we have to handle. So we require the parallel processing over there. And to compute, even though if we take an example of heterogeneity, then we have a lot of different machines, and we are handling their data parallelly, to which we have interfaced to a single machine. So then we require the parallel processing. Then we again, as I discussed in the very beginning, that we require to improve the hardware, like pipelining, superscalar, etc. But because these pipelining and superscalars are not non-scalable, but we require the scalable components, we require the scalable systems. So we need the sophisticated compiler technologies, we need such software which can handle these non-scalable activity components with this in the system. Though somehow the state vector machines are there, so vector processing works well for certain kind of problems we can handle. But somehow when we go for an NP hard problem and the multidimensional problem, again we got a problem that how the NP hard or the multi-dimensional problem can be handled. So there again we somehow some definite or differential vector solutions are available, some other solutions are also available to handle these large scale data efficiently, even though we have some optimum solutions which we can go for. But to handle these data, the hardware structure is required, and hardware is the first component which we need in parallel processing. Then multiple processes we need active simultaneously, as we are using nowadays octa processor we are using. So we can say that the 8 level of the simultaneous processing can be done. So lot of things are being going on, but still to make an efficient system, we still require to work on the kernel level. So, and proper communication and synchronization is required for its processes, and that forms the core of parallel programming efforts. So we now discuss with the processing elements and the basic architect of the parallel processing. Basically, the main elements we could say that in parallel processing are SISD, SIMD, MISD, and the MIMD. Means single input single data, single input multiple data, multiple input single data, and multiple input multiple data. So we have these kind of a number of instruction and data streams are being there. So single input single data is a conventional processor which we use in your 8085, 386, 486, and even up to the Pentium 102 we handle these things. But now we are using the single input and multiple data, SIMD. The data we are using in parallel process, we have data parallel processing, we can go for the some up to a level we have to handle the data in the parallel form, and the vector computing technology we have used. Then we have array of the systolic array, where we have the multiple input but single data is there. So how to handle that multiple data is how we use to handle the array, that is called the systolic array. But Nowadays we people are using MIMD, that very general nowadays it is, and we have the multiple approaches to have the multiple input and multiple data. So our current focus on the today presentation will be on the MIMD model, and we will use a general purpose processor. But I want to say that in this MIMD model we will not share any memory. This is the simple processor SISD, which in which the conventional technique, we could say, that which we used right from in the beginning of the when the computer was introduced, that we have a bit of data or the stream of data bytes, and they are being accessed sequentially. So we have data input, we follow the instructions, and then processor execute the data accordingly as per the instructions, and we get the data output. So speed was limited, and somehow we want to do any kind of another computational work. So the present execution has to stop. So interrupt were there. We interrupt the systems by using some, depends upon their priority, and we got an output. But somehow these are some example. Your simple PCs there, Macintosh workstations are there, but earlier days also some kind of a cluster form were used to make some supercomputing, and in that case also we used some parallel processing up to some an extent. But within a system, the parallel processing is we could say that in a revolution in the field of computing, and nowadays we people are using the MIMD. Similarly, here is an example of the basic architecture of multiple input single data, that we have data in number of data is there. We provide data the number of processor that, or we could say that we have cluster of the processor. Suppose we have 3 computers or 4 computers are there, and the output of 4 computers are being integrated to a single output. Then we could say it is a multiple input and single data architecture, and each processor is being executed by following their instruction set. That is your instruction of your processor A, then similarly instruction of your processor B, and in the same manner instruction of processor C are executing the same data which are being applied to the 3 processor, and then we are getting the output. So by using this MISD, even what we are doing, we are again increasing the computational complexity if we consider this MISD, because there is no worth that the similar data is being executed from a different processor, though our single processor is efficient and can be handle this data efficiently. But somehow to make a or more intellectual exercise are required, and then instead to depend upon the particular configurations. So some commercial applications are there, but somehow right nowadays we people are not using this MISD. But I think MISD architects has no use when single data is there and that is being handled with a multiple processor. Though we can say that the optimization can be done by using 3 processors or 4 processors, but when the same data is being handled by a single processor, then we require to handle the data with the SIMD is there. SIMD is your single input multiple data. Whenever you find any kind of a problem and you want to ask, you can raise your hand or you can ask me at any moment. Same for you all people who are watching me on this live. So then see here, now we have SIMD architectures. Now what we have done, we have the different streams of data. The data is being segmented. We had a bulk data and the data is being segmented into 3 groups or the 4 groups or the 5 groups, and that data is being separately handled by the individual processor. Now we could say that we had a bulk of data, or now we have used a cluster of processor, and that the cluster of processor is handling the streams of data. So that we are processing, and while processing that we are getting the output. And then here what we have considered here, that if the output of the CI is less than AI into BI, so that we can manipulate, the tuning can be done if the output is not is coming as per the processor. So then we could say that we support the multimedia processor over here. Now see here, now this is a revolution in the field of computation, and to handle data, we have multiple input and multiple data. So while handling this multiple input and multiple data, what is we are doing? Again, the same processor we have used, and the difference between SISD and SID, that instruction stream were common with the SIMD, but here you will find here that the instructions are also being provided individually. Now each processor is an independent source of computing the data of their respective stream. Now, what is here? The each processor is independent. They are handling their individual tasks. So best example is there. We have 4 or 5 tasks. A class of 60 students is there. So what we did? We make a team of the student, and then particular team has to do the individual work. So by doing that, so we are completing the entire task, or the task which the complete class has to perform within a very smartly and within a limited time. So we could say that we are not here. We can also say the memory that the tightly coupled with the MID, and the distributed memory that is loosely coupled with the MIMD. Then how the memories can we have in a huge, now cloud is the best example that we people are sharing the cloud with all in the parallel processing. Shared memory, then the MIMD machine is there. The each processor is sharing that proper global memory system. The data is lying in the cloud, then each processor is handling the complete data, but that is being streamed, which for the memory bus are for assigned to each processor, and they are handling. So by using this MIMD, what we are getting, we are easily can design any system, and we can handle the huge data, and we can overcome the problems which we had in the SISD. And some limitations are also there, that reliability and the expandability. A memory component or any processor failures affect the whole system. Because why it will be affect? Because the respective task which is being performed by an individual processor will not be completed. So that will affect the complete process. This is the main limitation of your MIMD. But somehow nowadays a lot of work is being going on by following the Morilla number of hardware structures, hardware configurations we are being increasing day by day, and the advanced processor are coming. So GPU processor are available. So some silicon example, the silicon graphics supercomputer is there. So which handle a huge data. Google is using, even your I can say that Google is the main who are using the silicon graphics supercomputers. And then I think so. I think some other companies are also there who are handling the who are using this silicon graphics supercomputer. But the GPU processor are being used to handle what happened. We use the GPU processor to handle the data, and the data which are being handled by simple computer took near about 5 to 6 days, but GPU processor simulated the data within the 20 to 30 seconds. So you can see that how the speed is increased from the 5 to 6 days. We are completing the same task in the 20 seconds. So this is the main advantage, and somehow we can say that we can communicate with your how the memory is being distributed in MIMD. We have our IPC channels, and each on the IP based channels are being used to distribute the memory, and then we communicate with the particular memory locations and handle the data. And network can be configured by using the either of the topology, whether it is a tree, mesh, cube, or any type of this. This is a mathematical laws of quotient. How we handle the speed of computer is proportional to the square of their cost. And you might be knowing that what Morilla says that every year people are increasing the number of transistors, and then we are decreasing the size of the processors. So here again also, if the cost is increasing, then the speed is increased the twice of that. If the speed is increasing, the cost is increasing twice of that. So but somehow the cost matters very low, but speed up by parallel computing is as the logarithm number of the processor. We are here example, speed up is equal to log of 2 of number of processor. Number of processor means the jitni speed the speed you want to increase, then the log of 2 into the number of processors. It means you need that number of processors is required to handle that.
That graph is linear.
That
Graph is linear.
which one is? You see the lower one, na? It is not linear. Lower one, logarithmic graph is lower one. This is your log of 2p.
I'm talking about upper graph.
Upper graph is not in log of that. Is just if the speed is increasing, the cost is increasing twicely. No, it is increasing twice. Speed is increasing. No?
Not power of 2,
Multiple of 2.
not power.
Okay, sorry. It should be power of, not multiple of 2. Sorry. Then the question mean the very fast development in the parallel processing can and relate area have blurred concept boundaries because a lot of confusions are there in the terminologies. Just like your concurrent computing, then programming paradigm is also a confusing part, that which language is to be handled. Suppose it depends. Suppose if we take an example of wireless sensor network, in a wireless sensor network also we are doing the parallel computing somehow. So we are handling the time US, means the operating system which we are handling. So again there is a confusing because we have a very limited space, and within a limited space we have to handle the entire thing. So while using this, and then parallel computing and the processing is also multi-processing, then how the computing can be distributed. So these are some emerging areas where we people are working, and we need to work on this. So it's hard to imagine a field that changes as rapidly as computing. Within a 10 years you can find what mobile you used 10 years before and what you are using nowadays. How rapidly the computing system is being increasing. Now you people are handling the GB in mobile. Your speed is your 4 GB or the 6 GB RAM you are using. So how fastly the computing system is been increasing. Nowadays we are using your I series of the computers, and this is the only field where the computing process or the computing is increasing very fastly. Means we can't think of that. And the 64-bit operating systems we are having now, you can imagine of 2 raised power 64-bit is the how much data we can handle single with the what is the size of your address bus and data bus. Though earlier we use only of 2 raised to power 8. We started with 2 raised to power 4, then 2 raised to power 8, 16, 32 and 64-bit windows we are using. So this is the only area where we are just changing the computing system so rapidly, and somehow we can say computer science is immature science, because some standard taxonomies we are not using, some standard terminologies we are not using, though we are using the techniques, but they are not being standardized up to an extent. Some standards are available, but still we require to provide. Just take an example of your IoT. If we take an internet nowadays, everybody is moving towards the IoT. But have you find ever any standard of IoT? There is no standard till date of IoT. There is no particular technology of your IoT. People are using it. Everybody is designing their own IoT. But we require to handle we require some standards so that we can make it generalized technique. Similarly in computer also, we can say that computer science is, that's why we quoted here that computer science is immature science. So even well-defined distinctions like shared memory and the distributed memory are merging due to new advances in technology. Somehow good environments for development and debugging are yet to emerge. We need some good environments. We need some good kind of structure. Hardware structure means we need structured hardware. Tiered architectures we require, which are not available. Okay, proper. So now we can say that there is no strict delimiter for contributors to the area of parallel processing. So these are some CEA operating system as high level language, databases, computer networks, all have a role to play, but strict delimiter is not there. So that, and this is the hot topic of research, where we can provide a fixed delimiters that it is generalized, which can handle your computer architecture, your operating system, your high level language, your even database, your networking, and they play in with the standard roles. Okay, so this is a hot topic to research, to provide a strict delimiter to the parallel processing. And then we need some operating system for high performance computing, because somehow while designing an operating system, we have to consider all the kernel level structures. Some structured level of designing are required. So yeah, you can see here that the type of parallel systems are here. What is that doing here? That we are sharing the memory parallelly, that smallest extension to the existing system. We have 4 systems. Server is the best example. That way server we use, we share the memory of servers. The system softwares are being installed in the servers, and we are using those servers, our systems. Then distributed memory parallelly, that the completely new system. There are 2 things, centralized and distributed. That your individual laptop is distributed systems which are using your own, but once it is connected to the networking and to the server, then you are using it as a shared as well as distributed memories. Then somehow some clusters are required, but while building up a clusters, we are increasing the hardware structure very large. Somehow building the clusters, we are increasing the cost of computing that data, and also we are increasing the complexity. Complexity means we have 15 to 20 computers, they are performing the same task. Somehow task may be same or task may be different to each unit, depends upon the requirement of the end applications. The clusters may be, cluster head maybe, the cluster head which we have considered maybe not so efficient to handle all the data. So a lot of issues are there. So to handle all the issues, the communication will become slow. So then operating system for this your MIMD, that the MIMD parallel processing system having thousands of processors requires operating systems radically different from current ones. Means we need that kind of an operating systems which can handle, because while we design operating systems, we need that each kernel level of your hardware should be properly integrated. Each layer of a hardware should be properly integrated, and the defined task of each layer should be properly will be handled and computed. So every CPU needs your operating systems, and we have to manage its resources and to hide its details. Traditional systems jo hai, they are your heavy, complex and not suitable for your MPP. So that's why we need some segmented processor, your core, dual core, your quad core, these kind of a processor. So we need some parallel core of your processor so that we can handle the huge bulk data. This is your hardware requirement while we design the operating system models. We need to framework that unifies features, services, and your tasks performed. What kind of features you want to incorporate, which services you want to have from that particular operating systems, and what task to be performed by the operating system is required. Basically, 3 main approaches are available, or it is required when we design any operating system, that monolithic operating system, layered operating systems, and the microkernel based operating system. Monolithic means the complete structure of your how to handle the complete structure. As I discussed, that each layer has their particular significance. The precision of each layer has to be controlled, so that the accuracy can be increased. and then the microkernel base means within the layer how we can make a proper communication. So example is a client to server and their operating systems. Then they are suitable for your MIMD parallel programming systems, and somehow simplicity is required, flexibility, even with the flexibility, the scalability is required, and the high performance are the main factors which required to while designing the operating system. Let's see how the monolithic operating systems we can design. As I told you that we complete structure is to be handled. So we have some applications programs, and we have the while designing these application programs, the system service we are using, and the hardware which we are sharing with each other, and then we are designing the user mode is your application program, and the kernel mode is your system and your hardware. Okay, so by using this complete utilization of the hardware with the system services, what we are doing, we are increasing the performance. By using this, we can have the better application performance. Then somehow difficult to extend, and your MS DOS is the example for this. I'm not then your layered operating system is there. We define each layer, and each layer has their individual task, and then they make a proper integration. Each layer make a proper integration with their upper layer or the lower layer, and then they communicate with each other and they perform their respective task. And then finally we go for the Unix is the best example of this, your layered operating system. And it is easier to enhance. We can, and each layer of the code access lower level interface with this, and the low application performances are there somehow. Then this is your traditional operating systems, operating system design, and completes her cheese. He has taken the entire everything and then putting a hammer on it and then breaking the system. So it is a very tedious task to have in this if we keep following our traditional operating systems. So that's why we are just improving day by day every operating systems. And a lot of, if we started with the window, what window we are using the 10 years before, and what, so basic fundamental is same, but the features are being what features we are extracting from window are the very updated and new features we are having. So this is where how the operating systems can be designed. Now this is a new trend in operating systems. We have some applications, server is lying somewhere, and somehow the sub servers are also, your cloud is the best example. And now we are using the very efficiently. There is no worry to handle the data. There is no need to keep the hard disk of the data and all this, and we are handling a very huge amount of data through this cloud computing. So this is a new trend, and somehow virtual computing machines are being coming. Virtual cloud computing is also somehow it is existing, and now we after 1 or 2 years you will find you can handle large bulky data through these virtual computing machines. Even though at cloud you can make your clusters. So somehow the day by day we are improving with the technologies, and so this is how the microkernel the client server operating system works. We have client applications, then we have your library file servers, that the network server is there, and then we display the server's output, and then then we handle all these things through your microkernel and the hardware levels. Send and this is how they communicate. So as I mentioned, the TinyOS kernel is there. The tiny means a small, and OS tiny operating system kernels are providing basic permittivity, the process, the memory use, then the IPC, and the traditional services become subsystems. Monolithic application prefers competence, and your operating system it is your microkernel plus user subsystems. Your Mac is there, the Parus, Chorus. These are some example of your microkernel client server operating systems. These are some popular microkernel systems: your Mac, CMU, Parus, CDAC, Cores, Connex, and Windows. So then again, if we start discussing in detail about your SISD, These were some examples, and these are some basic operating systems are available which we can handle now. Somehow, how to make a proper organizations of this multiple processor by you? Then we have, as we discussed, that we have single instruction and the single data stream, that is your SISD. Then we have single instruction, multiple data stream is there. Then MIMD, MISD. So let's start with your SISD, because while handling data, we know that how this SISD, and though we discussed earlier, but somehow in SISD we have instructions, and these all instructions are being handled by using single processor. Then if we consider that how the instructions are being executed, they are being simply executed in a single cycle. They are being streamed with the capacity. If it is 8-bit address bus, then the address location, 8-bit data bus, then 8-bit data. If it is 16-bit data, then 16-bit data. Then and data is stored in a single memory. Okay, and we have only a single processor is there, uniprocessor is there. And in SIMD, we have single machine instructions, and these we have controls simultaneous executions, means we are executing the simultaneously. So number of processing elements are there. Lockstep basis we use. Each processing element has associated data memory, and each instruction executed on different set of data by different processors. So as we discussed in the graphically or in the picture, that we had the 3 processors are there, but a single data is being handled by 3 processors. So we form the vector and the array of the processor over there. And similarly in MIMD, MISD, we have the sequence of data. Then we transmit it to the set of processors, 3 processor, 4 processor, depends what we are in. Then each processor executes different instruction sequences, and it has never been implemented. Now, in MIMD, as we discussed, that we have set of processors, and we can execute different instructions simultaneously, and we have a different set of data, and we can use the clusters and this your NUMA system or SMPS systems in your MIMD. Now, this is a basic taxonomy of your parallel processor architecture. In processor organization, as we discussed this, you have this all things we have discussed though, but let's we recall it, that we have SISD, SIMD, MISD, and MIMD. SISD is your uniprocessor, whereas your SIMD is vector processor as well as an array processor. Then your MISD has never been implemented. Multiple input single data technology never been implemented, because when we have multiple data, then each data has their own significance. Then we require that the respective outcome from the data. So it is not being implemented. So in MIMD, what we do, we have either the shared memory based or the means either tight coupled or the loose coupled. If it is tight coupled, then we are sharing the memory, and if it is loosely coupled, then we are distributing the memory. Then in loosely coupled, we use the clusters, whereas in tightly coupled, we use your SMP, yani systematic multiple processor, and non-uniform memory access. So these 2 processors are very efficiently be used, SMP and NUMA. So MIMD overview is, it is a general purpose processor, and each can process all instruction required, and further classified by method of processor communication. So each kernel can be communicated by their processor. So as we discussed, that if it is loosely coupled, then we form the clusters, but if it is a tightly coupled, then we are using the SMP. What is SMP? SMP is your systematic microprocessor, and your NUMA is your non-uniform memory access. So in SMP, we are sharing the memory. Each processor share the memory and communicate through the shared memory. Means we Then symmetric multiple processor are there. Then share single memory of the pool, or we could say the shared bus to access the memory. Then it is on the figure there, see here. Here you will find here that we are sharing the memory, sorry, distribute. We are here sharing the memory. We have simple memory, single memory is there, and we are sharing this memory. So here, then we can access and memory time to given area of memory, that is same, that will remain same, means each processor has the same time to access the memory individually. Okay, so then your non-uniform multiple access is your tightly coupled, that we are not defining the uniformity in the space assigning. It is non-uniform, anytime they can access the memory, and access time may be different. Okay, access time to access the different region of the memory may be differ. This is the only difference between the NUMA and the SMP. So if we consider the case of loosely coupled, then it is the clusters we use to form a clusters with the independent processors. They are, or your SMPs, then they are being interconnected to form a cluster, and then they communicate via fixed path of the network connections. So this is a limitation of the cluster, and if we follow the cluster parallel processing, then I think it is a minimum use. So this is the parallel organization of your SISD. This, I think we have discussed all these things through the parallel organization of your SIMD. And then your parallel organization of your MIMD, there we use the shared memory, and each that we have discussed earlier also. No? So then we have the parallel organization of your MIMD distributed memory. Then some symmetric multiprocessors are there. Then we could say that a standalone computer with the following characteristics is to be said to be a systematic multiprocessor. The two or more similar processors of comparable capacity, they're integrated with your processor share memory and input output. Processors are connected by bus or other internal connection. Memory access time is approximately the same for each processor, and all the processors share access to input output either through the same channel or different channel given paths to the same devices. So these all things are, we could say, for the systematic multiprocessor. Then these are the characteristics of your systematic multiprocessor, and all processors can perform the same function. Hence, they are symmetric, and systems are being controlled by the integrated operating systems, providing interaction between processor and interaction at job, task, file, and data element. So if we consider all these characteristics of a processor, then it is said to be the symmetric multiple processors. Then see here, we have three processes are there, and they are being executing the at different times. See here, process one is existing here, then dark is there, so it is existing. So they are sharing their time space at the different time. They are just multiple programming is being performed by a single processor. Okay, and here you will find the overlapping is being done. So SMP has advantages. First is their performance. If some work can be done in parallel, then the performance will be increased. Availability, processors are available since all processors can perform the same functions. If one failure, then the signal output will not affected. Failure of a single processor does not halt the system. And incrementing growth, user can enhance performance by adding the additional processor. Number of processors can be increased, and the scaling. vendors can offer range of products based on number of processors. So this is the advantage of your SMP. This is the simple block diagram of a tightly coupled processor. We have number of processor, IOs are there, main memory is there, and then we integrate through the interfacing mediums. Okay, so this is your block diagram for your tightly coupled multiple processors. Then the main classification of your organization is the time shared or common bus, multi-port memory, and the central control unit. So it is your central control unit and your the time shared or the common bus are being used, because here the individual buses are there, but we can have the common bus even also to share the bus, and the multiple port memory can also use. So what is the time shared bus? This is the simplest form of bus. Means a bus is available which can be shared timely. Structure and interface similar to single processor, and means a single bus is there which is interfaced with single processor, and but that is being shared. So following features provided means address, because buses are for that, either the address bus, data bus, or the control bus. Main three functions are available with your buses. So these are following features. So, and we are sharing the data bus, address bus, and your control bus. So what is means we are enhancing the capability of a single bus and also minimizing the hardware of the processor. So address, we have the distinct modules on bus. Then arbitrations, any module can be temporary master. Time sharing, if one module has the bus, other must wait and may have the suspend. So a single bus can be used instead of 3 buses. Now have multiple processor as well as a multiple input out modules. So to handle these IOs, multiple IOs and a multiple processor, we need the time sharing bus, that you remain at the halt, or you are the execution which is being presently going on have the low priority, whereas the thing which is to be coming up has a high priority. Then the present execution can be halted or the suspended temporarily, but the bus utilization is same. The same bus is being used. Okay. So here your symmetric multiple processor organization is there. We are sharing the main memory with the different IOs. So time share bus advantages are it is simple, simplicity, flexible, and reliable. So time share bus disadvantages are also there. That main is the performance is limited. Now the performance is totally limited, because depend upon the bus is available, then we can perform the respective task. So we have to be, this is the main limitations. And each processor should have local cache memory, which will reduce the number of buses accesses. Okay, and which leads to the problem of the coherences of cache memory. So we require such hardware which can be used, that the buses can be shared, but the coherence of the caches can be solved properly. So operating system issues are there while using this. We have some simultaneous concurrent processes are there. The scheduling should be proper. Synchronization, because common memory is there, we have to provide the proper management of the memory, and the fault tolerance and reliability is also required. So these are some issues which need to be incorporated while designing the operating system, so that the minimum number of issues can be raised. So this is your mainframe of your SMP. IBM Z series processor is available. So that it is a uniprocessor with one main memory card to a high-end system, and has 48 processor and 8 memory cards. Okay, so you can see that how much the hardware are being interfaced with a single processor, and they are being executed simultaneously. The dual core processor chip is there. Each includes 2 identical central processor. That we have discussed all these things, that we have dual core processor, the L2 cache memory 32 MB, then system control elements are there, which arbitrate the system communication and maintain the cache coherence. As I told you, that we need to design some systems which can handle the coherence of the cache memory. Okay, then Main store control is there. Again, how to make a proper interconnections between the cache memory and the main memory is required. Then memory cards are being used to store the data externally. They are being interfaced either to SSI or MSC medium. And then we have the memory bus adapters, MBA, that is used to interface the IOs channel, and they go direct to the L2 cache, depend upon the. So this is just somehow the basic structure of your. We have central processor, memory bus adapter, main store control, system control. So this is a complete structure how it works. Okay. Then cache coherence and MESA protocols. They are the problem, the multiple copies of same data in different caches. Because you can see here, the copying problem is again there. The number of the same data is being copied number of times. So how to handle and how to minimize the problem of copying of a data, same data to the number of memory is again required. So you can result in an inconsistent view of memory. Somehow consistency is required, and we write back policy can lead to inconsistency. So, and we can also go for the write through can also give problem unless cache monitor memory traffic, because traffic will be increased and it will be so. Some software solutions are available to handle this problem. Compiler and operating system deal with the problem. Then overhead transfer to compile time. We need to design complexity transferred from hardware to software. And however, software tends to make conservative decisions, inefficient cache. So we have to be consider that a proper utilization of the cache memory. Then we have to analyze code to determine the safe period for the caching shared variables. So these are some software solutions. Similar manner, we have some hardware solutions are available. As I told you that the coherence of cache is some protocols are required. Dynamic recognition of potential problems. Runtime has to be increased. More efficient use of cache. Transparent to programmer. Directory protocols are required, and the Snoopy protocols. There are some solutions which are available, and still we need to enhance. So these are some elaboration form of a directory protocol. What it does, it collect and maintain the information about the copies of data in cache. Means the replica of data can be handled by using the directory protocols. Okay, the data which are being copied number of times to the each cache memory, that can be controlled by using the directory protocols. So directory is stored in the main memory. Somehow cache memory can also be released by using this. So, and we can request to check against the directory. Then appropriate transfers are performed where to transfer data from the particular, because once we are systematically place the data, then that could be handled properly. Effective in large scale systems with complex interconnection systems. So for the large data, we can handle it, and the complex interconnection schemes can also be handled properly if we are using the directory protocols. Then Snoopy protocol is there, which is used to distribute the cache coherence responsibility among the cache controllers. Now, by using the Snoopy protocols, again the problem of cache memory is being handled. Then cache recognize that a line is shared. It also update and announce to other cache also. Then suited to bus based multiprocessor, and it also increases the bus traffic. Then we can invalidate the multiple readers are there, only one writer is there. Okay, so where to write? Then when a write is required, all other cache of the line are invalidated. So because only multiple readers are there, but one write is there. So writing protocols then has exclusive access until line required by the another processor. So rest of other lines will be invalidated. So used in Pentium 2 and PowerPC systems, state of every line is marked as modified, exclusive, shared, or invalid memories, and this is MESA. So we have to keep updated the writes. Writer has to be multiple readers and the multiple writers. Updated word is distributed to all other processors. and some systems use an adaptive mixture of both solutions. So we have to be consider all the constraints which are being falling within the system, that how we can enhance the efficiency of a systems by using these all operating systems level, hardware level designing, or your any kind of a system. So this is your sort of the how the properly we can share the data in MSS state. This is a transition diagram, that if we can see there that how if the data is being shared in which direction, in it is invalid in directions, then it is modified, then it is exclusive to this. So this is a read height, read mesh. So this is a system how the standard transition diagram of your MESI states. By using this MESI state, we are increasing the performance. Processor performance can be measured by the rate at which it executes the instructions, how many instructions are being executed and how efficiently they are executed. So we could say that the rate of MIPS is F into IPC, where F is a processor clock frequency in megahertz and IPC is the average instruction per cycle. That's why we say consider the what is the what frequency we are using, why we are considering the frequency 2.4 gigahertz is a frequency, because by using the frequency we can consider that how much time will be considered to execute a single cycle or the per cycles. So by using this we can increase the performance by increasing the clock cycles, and also increase instructions that complete during cycles. Number of instructions can be more executed. So somehow we can increase the complexity can also be increased and power consumption can also be more. So then multi-threading and chip multiprocessors are there. We go for that. The kernel level we have the multiple threadings levels are there. In hardware we use this threading process systems, and in this what we do, the instructions are being divided into some smaller groups. Threading is being done with the instructions and we executed these instructions in parallel. Okay, and by doing this, so what we are doing, we are widening the variety of multi-threading designs, and by widening this multi-threading designs, we are minimizing the computational complexity and accessing of the instruction will be fast. Execution. So these are some definitions of threads and processes, I think. Then how the implicit and explicit multi-threading can be done. Then and see here approaches to explicit multiple threading, and it is interleaved, blocked, simultaneous, chip multiprocessing. The time is a constraint, so I think I have to finish it. And then scalar processor approaches are being used. Single threaded scalars are there. They are very simple pipeline, as we had used in some question. Okay, some questions were there.
No, sir, they just got reconnected.
Okay. Then we have the interleaved multi-threaded scalars are there. Then we could say that the easiest implement to the multi-threading. Then the simple pipeline can be used, and then the blocked multi-thread scalars we use. So here the diagram how the scalar how the single threaded scalars can be executed, how the interleaved multi-threading scalars can be used, and how the block threadings can be used. So here repetition is there. What we are using? We are using blocking these threading systems. So multiple instructions issues are there. I think we should just have an overview of this. They are superscalar. In superscalar, there is no multi-threading. If it is interleaved multi-threading superscalars, then each cycle can have as many as instructions as possible issued from the single thread. Then we can delay due to delays is being increased due to the thread switching eliminated, and in this number of instruction issued in cycle limited by the dependency. So these are some. Then we similar in the block type as we discussed in this diagram that we have elaborated here. Similarly, the MI diagram is there, that we have superscalar is there, then interleaved, then how very long instructions are being used. Then we have some kind of an superscalar architecture are required. Then okay. Similarly, the parallel simultaneous execution of multiple threads can be executed. We use the multiple processors. Chip multiprocessors are required, and each multiprocessor has two issues: superscalar processors, and each processor is assigned a thread. Depends upon which. So this is a parallel diagram. That this is your simultaneous multi-threading, and here you will find your chip multiprocessor. They are being divided in this, and we are extracting the same data. So by dividing this chip multiprocessor, we are increasing the speed, and we can easily access the data from the bulk of the data. So example of this, your Pentium 4 is the best example. Intel call it hyper-threading. Okay, then SMT will support for 2 threads. Then single multi-thread processor, logically 2 processors. Your IBM Power 5 is your high-end power PC, which combines chip multiprocessing with SMT, and it has 2 separate processors. Okay, so this is your Power 5 diagram. Then we form the clusters. Again, we discuss all these things. Benefits of clusters are that they are scalable. Absolute scalability can be there. Incremental scalability, high availability, and superior price performance. So here you can have an example of how the cluster can be formed with the server and the other servers, and we use the high-speed message links over there. Somehow nowadays we are using the small radios over there. Then RAID modules are being used to minimize your high-speed messaging services. So these are some operating system design issues. We have to maintain the failure management. Then the load balancing is also required. Then I think so. How the cluster computer architecture, it is a block diagram that we have a high-speed network switch. Either your Ethernet or other optical fiber cables are being used, and we have some different power stations are available. And then we are building a clusters with the middleware, and then we are executing the data sequentially or the parallel. It depends upon the data. So these are some cluster middlewares, and but somehow people are also using the blade servers. Nowadays people are using the blade servers over there. So they are common implementation of clusters. Blade servers right nowadays are being used very efficiently, and server houses multiple Google is also using the blade servers. Okay, it space the save, and it improves the system management. Chassis provided power supply, and each blade has processor, memory, and a disk. So by using this, the hardware infrastructure is reduced very low. See here, this is an example of 100 Gbps Ethernet config with the massive blade servers. Okay, and your telephone exchange are the best example of the blade servers. Then so this is then your non-uniform memory access. I think we should here is an example of your NUMA, that we are being interconnected with the number of servers, we are building we have the 4 or 5 main servers, and they are being connected with. Then cache coherence, we discuss all these things. Then the NUMA pros and cons, that the effective performance at higher level of the parallelism than the SMP. No major software changes are required in your NUMA, and performance can break down if too much access to remote the memory. So these are some of the pros and cons of your not transparent system is there, and availability is very low. So then we go for the vector computation. I think this is your we have 2 vector additions example is there, and we can, so it means we have the number of array, so sorry, number of components in the array, and then we are combining to a single unit. Then approaches for this vector approach is that we use general purpose computer, and we use the iteration to do the vector calculation. Iterative calculation work is being done, though it is time consuming, but somehow we can use this one also. So in processor designs, we require the pipeline ALU units within the operations and across the operations. Then parallel ALUs are also required, and parallel processors are also required. So somehow how we can use this, it is available here, that pipeline ALU is there, then we have the parallel ALUs are there. So then to make a supercomputer, we require the chaining. We have to create the supercomputers, then combining all the big computers, the vector operation may be start to as soon as first element of operand vector available and the function unit is free. The result from one function unit is fed immediately into another, and if vector registers used, intermediate results do not have to be stored in memory. So these are some computer organizations how the chaining can be done. Single control unit and a multiple control unit. In single control unit, we have uniprocessor, pipeline ALU and a parallel ALU. This, as we have seen in the figure in the previous slide. And multiple control units, we have just multiple processor and the parallel processor. So this is the somehow the best vector facility available with the IPM 3090, that we have main memory, cache, then means a complete setup is a complete CPU is there, which forms the vector type of the processor. So with this, we conclude with the today's lecture. If you have any doubt, you are welcome. Same for all the centers. If you have any doubt, then you can ask. So
Yes, we have any doubt from all the nodal centers? Yes, from BITS Pilani.
Sir, it's BKBIT Pilani, and we all are all clear, no doubt from our side.
thank you, thank you.
Yes, from any other centers we have any doubt? For this center?
Thank you.
Right, sir.